delighted to introduce the inaugural speaker, invited speaker of ICAPS 2025, Hanna Kurniawati. She has had a very long career working on two notably hard problems. I don't know, what do you think is harder, POMDP solving or motion planning?
Equally.
Equally hard, no? So just to make it more interesting, looking into the intersection of these very, very challenging problems that have lots of really obvious applications into the development of safer, smarter, and more useful autonomous systems. So we are delighted that you accepted an invitation, so thank you very much. We wanted to recognize your long and distinguished career, and we also truly really wanted to learn it all about the very good work that you guys have been doing at NNU in the last years. Thank you very much, Hanna.
Thank you. Okay, well, first of all, thank you so much for inviting me here. It's a great honor, and thank you so much for the kind introduction. And thank you for coming here this morning. I know the alternative is nicer. Okay, so I'm going to talk about handling uncertainty in robot planning, including in motion planning. Perhaps I start with this. For those who have worked with robotics, I think it's very clear that we need to handle uncertainty, actually various type of uncertainty. And the risk of not doing that is some pain. That's an example, my sort of early encounter with uncertainty and some of the pain that we need to handle. So this was when I was doing my postdoc. During my PhD, I worked more on geometric motion planning. And then during my postdoc, I start working on marine robots. We have surface vehicle like this, and underwater vehicle that we want to operate in this kind of environment. Sorry for the video. That's basically taken from a barge. So that's why it's quite not exactly high quality. But so what I wanted to say here is that there's so much different types of uncertainty that we need to handle if we want to be able to operate reliably in this environment. Of course, from the environment, water current changes in the water level. So the changes in the water level affects our ability to go into this kind of places, for instance, depending on the level of the water, we might not be able to go through there. And we did use prediction on water current, on water level, but at the time, at least, the accuracy that we can get, at least based on the marine scientist calculation, the accuracy is only up to the next 3 to 5 minutes. And this kind of mission usually lasts for 30 minutes or so. And then, of course, there's many other types of uncertainty as well. If we accidentally bump onto the boundaries of the structures, then that rudder usually turn a little bit, and that basically changes the entire effects of your actions significantly. So it's not just small noise anymore, right? And of course, there's perception. This kind of water are murky water. If we use camera, that's going to be problematic. It's unlike the water in Gold Coast, which is nice and pristine. And of course, all of these are from the motion planning side alone. Once we start wanting to coordinate among different robots, we have issues with communication. Once we want to have human in the loop, that's even going to be more troublesome because we need to figure out what's the intention of the human, which is not that easy to consider. So all in all that I wanted to say is that there's so many different types of uncertainty we need to handle, even in just this single robotics task. But of course, we do want robots to be able to be reliable, and we do want different types of robots operating in different types of environment as well. So for us to be able to do that, I think there's at least two main components we need to have. One is definitely we need to have capable robots itself. So in here, the focus of my work is more on how do we enable robots to generate strategies that can accomplish its task well, where well means that it's reliable, robust, adaptable to uncertainty, to changes in the environment, scenarios. And the second is that when we want the robots to operate in our environment, definitely we need to have some kind of acceptance from the human that, yeah, we can use this robot, and in here we can look into a bit of the assurance from the user point of view that, okay, I'm going to use these robots and I sort of am okay with that. And what's interesting to us is that in both of these components, it turns out sequential decision making under uncertainty, this similar approach actually applies to both. And I just want to mention, I'm using the word sequential decision making here just to be able to cover both the planning and learning techniques and the integration between them. So I'm going to talk one by one. And perhaps I wanted to, when we talk about robots, we always think about actually having physical robots. And when we want to develop that kind of capability of enabling these robots to operate well, of course, we want to be able to apply that for various different types of robots in various different environments. But there's actually broader types of problems in robotics, including those that does not have the robots in it. So if you were here on Monday and you attended the PlanRob workshop, William Jones presented our work. This is a preliminary work on trying to automate dry docks, the Garden Island dry dock. So it's actually to maintain ships. Right? In particular, what we did at this point is trying to figure out how to reconfigure this kind of kill blocks so that it can maintain the position of the ships quite well during the maintenance of that ship. And the idea is that we do want to put in as many ships as possible and with minimum arrangement costs. And this is sort of the size, the scope of this. Perhaps this is just a part of it. And the idea is that how do we rearrange the different kill blocks so that it can support the different ships, and also how do we move these different kill blocks depending on the scheduling of which ships comes in. And in here, it would be nice if we then put in robots to basically move these kill blocks, but I think for the foreseeable future, we still have human drivers driving this kind of vehicle and lorry and moving the kill blocks around. So what we need to develop are plans for these kill blocks to be moved that then we will provide to the human driver. Right? And of course, ideally, we will account for what the maneuvering they can do and the potential disobedience of the human. That's, this is an example. What I wanted to say here is that this remains a robotics problems. So when we talk about robots, the agents work in physical world or in simulated physical world, even if we don't have the robots as we think robots looks like. So the goal of the sequential decision-making capabilities we want to have, as I mentioned, it should work for various scenarios, environments, variety of robots, including when the robots are humans. And of course, this basically means we want a general purpose decision-making capability. And so we are looking for frameworks that can do this general purpose sequential decision-making. And fortunately, we do have that for quite some time. Partially observed Markov decision processes are frameworks that is indeed designed to account for variety of types of uncertainty, right? And essentially what it is just a mapping from observations to actions. And in order for us to do that mapping, the main thing here is that it uses state estimate, which is, sorry, oops. Yeah. State estimates here, which is not a point estimate as many of the other frameworks are, but it says, well, I don't actually know the states that I'm in because of the effects of emotions are uncertain, because of my perceptions are uncertain. Then I'm just honest, I honestly don't know which state I'm in, and so I represent it as distribution over the state space called beliefs. And then the policy that I have are computed with respect to this distribution over the state space. So essentially, that's the main thing on about POMDP. And in order for us to do that, we need at least three things. One is some kind of model, or actually stochastic model of the effects of actions, which is the transition function. The model for uncertainty about what kind of observation will we get given the states we end up. Sorry, there you go. Given the state we end up after performing actions, so this is essentially likelihood of observation and reward function from where our objective function will be derived from. Right? And in here, planning just means that I want to find the best policy that maximizes the expected total reward. There's many different objective functions on how this expected total reward can be written. So the one that I will be talking about is this type of objective function, which is the infinite horizon objective function with discounted reward. And so one thing perhaps I want to mention, in here, we assume the state space are discrete, action space are discrete, observation space are discrete. But these days, we can handle continuous spaces, including continuous space, observation, and actions. If we have continuous state and observation spaces, then this summation just becomes integration, and the PMF, rather than having PMF, we will have a PDF, right? And that's pretty much it. But in this objective function, what's important is just these two components. One is the easy to compute, which is the immediate reward here. The other one is the hard to compute, which is that I need to figure out what's the expected total future reward is. Because as we mentioned before, this is a sequential decision-making problem. So we do need to consider that the actions I take now might actually affect what I can do in the future, and that comes into this component here. And what this is doing is essentially, if I start not knowing which state I'm in, I might be in various different states, right? From those different states, I perform a particular action, and because of uncertainty in the effects of actions, I will end up in even more diverse actions. And from those different actions, I might see different observations, and that's just a single step. But in many robotics problems, we do want to look ahead of a large number of future steps. So suddenly, this part needs to consider exponentially many possible futures. And that's intuitively the difficulty in some of the solving that we need to do, which in the worst case, solving this exactly is indeed computationally intractable. But in practice, well, we have done quite some progress. So this is before 2003. This is a simple problem of navigation with just 12 grid cells, right? And this takes actually around a week to solve. In 2003, there's this sampling-based method being introduced, which basically gives us a jump in the capability. So this is a robot finding problem with 870 states, but it takes 50 hours. And then, because this is a sampling-based methods, we realize that if we improve the sampling in a particular way, we can actually improve the performance significantly. And for the same problem, we can generate a better policy with just 6 seconds planning time. And after that, we can start solving problems with hundreds of thousands of states in just 2 hours. And all of these are offline methods. So these times are computed before execution, which for robotics, that's all right if we have some good models. Right? But then after that, usually the issue with this is the memory hits the limit very fast. And so after that, there are many methods for online solving of POMDP, approximate solving of POMDP. And in 2018, we happened to have both SIMPAR and ICRA, a robotics conference in Brisbane. So we managed to collaborate with Keynote, which is the maker of this robot, to showcase the POMDP progress. And that's basically the entire motion planning of this robot, which is supposed to pick up the cup. And it needs to pick up in a proper way because then it will use it to scoop candies and then give it back to people. So this entire motion planning is done using POMDP. Online POMDP planner we developed with planning time per step of 0.7 seconds. The reason for 0.7 is because that's the amount of time to execute the actions. So that's the thing. The state space here is 6-dimensional continuous space. The action space, we simplify that by increasing or decreasing the joint angles for each joint, because this has 6 degrees of freedom. So then basically we have 2 to the power of 6, and plus the open close gripper and the scanning of the environment. And so we run this live demo 7 consecutive days, 10 hours per day. And that resulted in more than 150 runs, where we get more than 95% success, where success basically means that we can properly grasp the cup, scoop the candies, and give it to people. So that's pretty much from there. The types of uncertainty we handle here are, well, basically the blurry vision of where the cup position is, and the perception we have, we sort of deliberately didn't do much work on the perception. This is really, we took an off-the-shelf perception method and just plug it in, and I'm pretty sure we can do better, but one of the things we wanted to test is how far can we stretch if we don't do anything with the perception side. And the other side is the human. If we are going to do a live demo in robotics conference, we do need to handle this kind of nasty audience. There you go. And so that's the biggest source of uncertainty. So Marcus Horger and Josh Song was the students working on this, and they did try a lot of this kind of making it robust against humans. Okay, so that's where it was in 2018, and perhaps this is time I will talk a little bit on what's the tricks behind, and then later I will talk about what our recent exploration in this. So the tricks in here is we didn't actually strive for optimality. So it turns out that in many robotics problems, some approximation of optimality is often good enough, because in many of the cases in robotics, there's no explicit accounting of the uncertainty. So if we just account for it a little bit, then we can get more reliable and more robust behavior. And the second one is that there's actually many useful structures that often, in motion planning, for instance, when we think of structures, usually it's more on geometric structures, environment structures like plants. Right? But actually, there's other types of structures that we have. If we use one robot with the same sensors all the way through, then there's definitely going to be correlation of errors between the different scans, for instance. And then there's also the nice thing of working with motion planning, so it's hard and easy at the same time, because we have continuity of motion. So I know that if I give the commands to my robot to move 1 meter forward, I know that it's not going to move exactly 1 meter forward, but by the same time, it's not going to jump from Canberra to here in 1 second, or at least we cannot do that yet. I don't know if you will ever be able to do that. So that's a nice thing that we can utilize as well to reduce the search space that we have, right? And there's also some properties that we can exploit as well, like some parts of the variables are fully observed, and some others are partially observed, and some of these variables are often dependent to each other, and so we can start exploiting some information between different variables. So the details of this, there's a lot of problems we need to solve. And so this is just some of the methods from our lab. By no means there are many different methods that have been proposed. There are many great works that have even been proposed before I even started working on this. But this is just to see what we have done. And perhaps because of the immense work that have been done, we did some summary of what people have done so far in this review paper, at least since the introduction of the sampling-based method, so in 2003. So now I wanted to go a little bit deeper on some behind the scenes, especially the primitive computations that we need to enable this improvement in the practicality of POMDPs. And I will talk perhaps a couple of things on the primitive computation, and then I will talk briefly about the modeling side and the integration between the two. So in terms of the primitive computation, so I'm going to talk about this complex dynamics first, which is basically problems where the transition dynamics for that one, even one step forward simulation is costly. Right? So in many, or at least in almost all of the POMDP problem benchmark we have seen, we didn't actually encounter this kind of problems, which when we apply it to robotics cause quite a bit of an issue. So why is that the case? So if we look into the typical approximate POMDP solver, including offline and online, we essentially these days sample beliefs, right? And in order for us to sample beliefs, we sort of assume that we know the initial belief. And what we did was, well, we just select actions and then sample observations. And then once we have that, we get into the next belief. So essentially, this belief tree maintains those sample beliefs where the nodes are beliefs. The edges represent action and observation pairs. And the next belief, basically, if is basically the evolution of this belief after performing this action and perceiving this observation and get into this next belief. And in order for us to get the next belief, basically, what we did was we often samples a state, so sample particle of the belief. So we represent the belief as particles, or even if parametric distribution, we can sample from them and get a state. Then we can use a generative model to figure out what's the observation, the next state, and reward function we could get after we perform certain action from that state. Right? And of course, if we get the same action observation, it will be clustered together into the same belief node. So that generative model of getting into the one step forward simulation essentially requires us to figure out what the next state is, which if we have complex dynamics, that basically means solving a differential equation to figure out what's the next state given action and the current state we are in. So that part there can be quite expensive depending on the problem. And this is an example. This is a typical, this is a famous POMDP benchmark rock sample, which is a simplified version of the problem of Mars exploration, trying to figure out which rocks to sample. So these black ones are rocks. Some of them are good, some others are bad rocks. We want to sample the good rocks, of course. So in here, the transition dynamics is almost instantaneous. It's just factor displacement, right? In here, we have a manipulator arm, and we do force control. So in order for us to get to the next state, we do need to solve the integration. And this is the total computation of one step forward simulation compared to the total planning time that we have. If we use this, which is typical of almost any POMDP benchmark we have, we actually take less than 10% for this computation. If we have this problem, suddenly this proportion actually goes almost 90%. So what that means is that what we expect to be able to run this and get many forward simulation, suddenly the number of forward simulation we can do is very, very limited. And of course, what that means is that the estimation of the value function, the policy that we eventually get is quite bad as well because of that primitive. So now, you might say, well, this seems like a control problem. So maybe just look into what those people in control did. Many of them simplify the dynamics into linear system. And then the belief, if you have linear system, then the belief is assumed to be Gaussian and everything is nice. That works if you work in control problem where the space is usually quite open space. But when we want to work with motion planning problems, we want to work near obstacles. We want to work near the boundaries of the capabilities, essentially, right? So that actually causes the bifurcation. So basically, I no longer have unimodal distribution. If I have obstacles here, I might bifurcate to either side, right, if I move that. So that basically makes it difficult for us to apply linearization and Gaussian assumption. And so what we did instead was that we look into, can we actually use some techniques from the what's so-called multi-level Monte Carlo to sparingly use the expensive high-fidelity simulator with many low-fidelity simulator, which is cheap. So this is the work by Marcus Harger, who was my PhD student at the time, and now he's my postdoc. So in here, we basically combine the original complex dynamics, which is expensive, with this very cheap dynamics that, well, we can run very fast. And it turns out that multi-level Monte Carlo provide us with a framework for actually doing this that will eventually, that is guaranteed that to eventually converge to the actual estimate. Right? But the catch is that we need to have correlated samples, correlated pair of samples between the different level of fidelities. So the different level of fidelity, if we use physics engine, for instance, if you use MuJoCo, it's actually pretty easy to get. So basically, you can think of that as the different level of discretization. Right? So if it's a differential equation solver, an integrator, so any physics engine are essentially an integrator. So you can actually solve it as numerical integration. Then that essentially boils down to the discretization you do, which if you use MuJoCo and those kind of things is sort of the delta t parameter. Right? So if you use small delta t, you get higher fidelity. If you use lower delta t, you get lower fidelity. So you can play with that part. There's a limit to it, but I won't go into the details of that. But so that's pretty much the idea. And if we run this into the typical online software, essentially we can start by sampling the episodes, of sampling forward simulation using the courses, so basically using the lowest fidelity. So that's very bad, but very fast, right? So the estimates that we get in terms of the next state is not going to be good, but well, later it will be average. Then after that, we sample a particular fidelity level, and this is where we are going to put in the correlation of the different fidelity levels. So in here, if we take one fidelity level, then we are going to sample correlated episodes, which is based on the same sequence of actions. Right? So that's one way that we can get this correlation. And once we have that, if we apply to some problems. So this is actually a simplified force control for 4 degrees of freedom robot. And this is the KUKA robot with force control, so that's 6 degrees of freedom. And this is second order dynamics of car-like robots. And this is the similar robot to the one that we use for the Candice Cooper problem. So we can get a much better result with this because in all the forward simulation dynamics, we actually spend a very small proportion with the high fidelity, and the rest are using low fidelity. So if we compare this with POMDP, ABT, which is the state of the art at the time, then we can actually, with just 1 second planning time, we can straight away get a very good immediate, well, total average discounted reward. So that's in this side. So the next one is a new line of exploration that we did in my group, which is that one of the issues in solving POMDP solver is the interleaving between the maximization and the estimation of expectation. Right? And so in this line of work, we try to remove the need for that maximization. Why we want to do this? Well, this is a seemingly simple problem. So this seems like a simple problem, right? I just have a navigation problem. So this is much simpler than that Candy Cooper problem, for instance. So I can start from either this side or this side of the map. And the goal is to reach that G1 or G2. Either one is fine. Every step does have errors in the motion, but then I can localize at this area marked by pink. And there are some danger zones in here that are marked by yellow. So the idea is that if I use heuristic that simplify the problem, for instance, to MDP or to deterministic problem, then I can actually go from this side. This is actually a shorter path to the goal, and it's pretty much okay because I have full observability and I can figure out how to navigate through this small passage. But if I have partial observability, then going through here is actually a disaster because there's a big chance that I'm going to fall into those danger zones. And so the way to do it is I'm supposed to go all the way to the right and then go back again to this part of the environment to get to the goal. And that basically requires me to have at least 60 steps, 60 forward look ahead steps. We tried this with POMDP, and instead of giving just 1 second planning time, which is today is quite common for online POMDP solver, we give them 30-second planning time per step. We also tried this with Magic. So Magic is Dashpot, which is the competitor of POMDP, so state of the art online POMDP, approximate POMDP solver, but Magic actually adds Dashpot with learn macro actions to basically try to reduce the effective planning horizon. This is the result. So basically the success rate of POMDP is 1%. The success rate of Magic is 0%. It seems very simple problem, right? So, so the difficulty is that if we go back to this objective function, so let's ignore the easy part for now. So we just have this, right? This and that one. So in order for us to get a decent estimate of the expected total future reward, that in itself takes a while and is somewhat expensive computation. So what that means is that if I want to apply gradient-based optimization, which is sort of the state of the art for optimization, right, the fast method, well, I can't actually do that because the estimate can be quite bad, at least in the very beginning, or I will need to wait for a long time before I start doing the gradient ascent or descent. So what most of the current online approximate POMDP solver does is actually they do a sweep over the entire action space. Or even if they don't do a sweep over the entire action space, they will eventually do a sweep over the entire action space. That's if you're familiar with POMDPAO and things like that. So essentially, they rely on this sweeping over the action space, which of course is very expensive to do. And if we either have long horizon, which requires this computation to become more expensive, or we have large action, then the problem becomes terrible. So what we try to figure out is that can we get away without that max operator? And this is the work of my postdoc, Edward Kim, and my PhD student, Hanna Kurniawati. So what we did here is that it turns out if we start with some kind of initial stochastic policy, and we add this term here, which essentially penalizes how much we deform that initial policy, we can get to converge to this objective function. So it's a transform objective function because we have the additional component there. But in order for us to do that, the optimal value function with respect to beliefs turns out to look something like this. So I can get rid of the maximization, and in here basically is expectation over this function. So you can think of this as akin to Q value function, for instance, right? And I can get the optimal policy as well, again, without the max operator. And so what we end up here is that the computation we need is really just estimation of expectation, which the entire field of Monte Carlo has been doing this. Right? So we can benefit from that. Now, since I've seen quite some RL here, so I guess you might say, well, that equation is not that uncommon in RL. That might be similar to log sum Fs, for instance. Yes, it is similar equation. So we indeed expand this from what's called linearly solvable MDP. But many of the expansion in RL, or most of all of them, are basically two state space. So it still assume full observability. And that is very related to what's called max entropy RL. What we did was we expanded to partially observed scenarios. So all the mechanism there are actually done with respect to beliefs rather than with respect to states. So that's the expansion that we did. And if we go back to this problem, so if we don't do much smart search, we just rely on some initial reference policy, which may not start good as well. We already increased the success rate to 30%. Still not great, but compared to 1% or 0% is an improvement. And we then collaborate with Lida Kavrakis' group, who recently developed a parallel collision checker, factorized collision checker done on CPU only, which is FAM. So this allows us to integrate the POMDP solving with the sampling-based motion planning in a very seamless manner. So what that means is that rather than having a single action that we forward simulate, we actually use the edges of PRM or RRT. So basically, so I'm not sure if everyone is familiar with sampling-based planning, but I can imagine. Right. So basically, if we construct, in sampling-based motion planning, we construct connectivity of the free space of the configuration space and represent it as a graph where the nodes are configurations and the edges represent sequences of actions to go from one configuration to another. So it turns out I can lift up that sequence of action, that edges, to expand my belief tree. So now when I'm expanding belief tree, I'm actually using that sequence of actions rather than a single action. And that allows us to solve this problem with about 90% success rate and with just 1 second planning time per step. So a combination of the transform objective function and the way we do the search to reduce the effective planning horizon basically helps us in doing this. And the next question becomes, well, this is still solving the modified objective function of POMDP. So of course, what we want is to solve the original POMDP objective function. And it turns out we can converge to the original POMDP value function, the original objective function of POMDP, which is that we just need to iterate over the reference policy that we set. So rather than having a single reference policy in the beginning, then what we want is to be able to reuse that. So we get an improvement of value function, and then after that, we refine the reference policy, and we do this iteratively, and it will converge to the original POMDP solution eventually. So this is again the work of Edward Kim. Now what's nice is that if I remove that max operator, that allows me to do easy parallelization of approximate POMDP solving. So this is a very new work by Marcus Herger, who is now my postdoc, and Rafi, who is my PhD student. So it used to be, if we want to parallelize POMDP solving, the issue is the scheduling between the max and the estimation of expectation. And there are methods to do that. So for instance, the Hype Despot, and there's also parallel POMCP that tries to do a very careful scheduling of the POMDP solving so that we can do parallel POMDP. So because we have removed the maximization operator, then it's actually easier for us to do parallelization, and we can just factorize everything. So it's flattening it out, put it in factors, and it's really the usual way that people in machine learning basically pass it to their GPUs, so that we can do that here as well now. And if we do that, so we test this on navigation in partially observed environment with, that's the number of state space that we have, and then the multi-agent rock sample. So I mentioned about rock sample benchmark earlier. This is expanding that to if we have more than one agents. So that's why the number of states becomes so large, and also the action space becomes larger. And so with this way of factorization, with this way of parallelization, we basically can get better policy in 0.05 seconds, so 20 times faster than the Hype Despot. And if we then run for the bigger multi-agent rock sample, so we have much larger action space, much larger state space. We try Hype Despot, it crashed. We didn't try the parallel POMCP just because we couldn't find the online, we couldn't find the software. They didn't release that. And then, yeah, but in our case, Hype Despot crashed in here, and in our case, we can still get quite a decent result. So this is still under review. This is a very new work, but I think I'm quite excited about this because we can now have all the power of GPU that people in machine learning have been exploiting so far, and we can do that easily as well. So that's what I wanted to say about this primitive computation. So components of the solving of the approximate solving of the POMDPs that seems to be small, but it can have a big impact on the overall solving. So like removing the max, and then previously it's just about utilizing the low fidelity simulators for the one-step forward simulation. So now I'm going to talk a little bit about the modeling. So we do have a work where we do an end-to-end model learning together with planning, but I'm not going to talk about that. I will just talk quickly about the transfer of policies, of POMDP models into different scenarios, because usually when we talk about POMDP, the first thing that people will ask is that, well, the POMDP model is also only for specific problems, right? So not exactly. So this is the collaboration we have with Woodside. They want to be able to open and close valves, different types of valves. The idea is that rather than sending an engineer to potentially dangerous place and with very expensive OHS, if they can have a robot station there, then it's supposed to be safer for the human. The thing is that these valves here, so this is actually the valves they sent us to our lab for testing. So the valves that they have are not pristine valves that we often see in many robotics testing, but they are actually uh, already quite worn, and the and there's rust everywhere, right? So basically, in order for us to open it, just like our plumbing at home, we don't want to just push the force to as high as possible because that might cause a burst. And of course, the burst here is not just water. So that might be dangerous. So we try this in our lab, and in our lab, we only have this kind of robot arms and hands. So from our collaboration with Kinova. But in the Woodside lab, we actually need to use their robot, which looks like this, which is UR10. Uh, and so in here, all the POMDP models we use in here, here, and here are all the same. The only thing that changed when we move to different places is the URDF model of the robots. So basically, that's the kinematics models of the robots, that if we buy robots these days, they would provide us with that URDF model. But the POMDP models, including the reward function, transition function, and everything else, remains the same. So the reason we can do that is that because POMDP uses beliefs, it is actually more robust to errors in the models itself as well. And so that's basically what we have there. Sorry. Yeah. So I will just very quickly talk about. So there is also a need for us to consider primitive computation that accounts of the kind of models and the representations we use. This is a very recent work that my student Jingyang Yo just presented a few weeks ago at IROS. So we want to be able to do inspection, autonomous inspection of this kind of structures. This is from a glycol distillation plant. And that's the number of triangular faces of this model. The original, so this is just 1/3 of the environment. The entire environment has about 90 million triangular faces. So if we do next best view, because of the many occlusions, usually it won't actually cover well. And so we do want to have a longer horizon look ahead, and we need to do inspection planning, which usually requires quite a lot of memory. Because we need to maintain the coverage information. So there are actually better representations of the environment, which is called neural SDF. But all of the inspection planner today, if we want to use this neural SDF, needs to do conversion between explicit and implicit model. So what we propose here is that we propose primitive computation, so collision check, coverage check, observation. So this is of simulating what might happen if we observe from certain areas. And all of these are basically done with the implicit representation itself. And if we do that, then we actually gain memory improvement by about 70 times, reduce memory. And that allows us to start working on this kind of problem and including the full scale of the plan itself. We did a bit on the extension of POMDP to multi-agent, in particular in developing the framework to ease integration between planning and learning in here. So if you are interested, you can take a look at that. But I'm going to move on quickly because I have been shown that I have limited time now. Okay, so now I'm going to move quickly to the assurance of the systems from the user point of view. So what we are looking in here is not that we are trying to guarantee certain level of safety, but what we want to be able to do is just that if you give us multiple different autonomous systems, robotic systems, we don't need to know the internal of the hardware, the internal of the software. Can we figure out which of these systems are more effective or safer under certain metrics? So that's the point of view that things like NCAP has taken. So that's sort of, we try to follow this way of looking into safety assurance. So this is what I was mentioning before. we want to be able to rank the different systems. That systems include both software and hardware based on some kind of metric, for instance, in this case, based on safety. So to be concrete, we take an example of an autonomous car, and this is an example of avoiding collision with pedestrian crossing the street. Right? So what we observe is that if we look from the pedestrian point of view, if the pedestrian have a safe trajectory to avoid collision with the car coming in, and then we try to deform this trajectory as minimum as possible so that the resulting trajectory causes collision, then there's actually less margin for the car to make errors. Right? So that's sort of the intuition behind this. What that means is that now what my POMDP agent is doing is actually controlling the adversary, so in this case it's the pedestrian, and I'm trying to figure out how to deform the safe trajectory as small as possible so that I can cause collision. And so if I can do that, accounting for the other, the car as partially observed system that I have no idea of their behavior, then I can start generating strategies for the pedestrian to collide that is still respecting the original safe trajectory, which also means that in many of today's methods for assessment, some of them do rely on accident data, which is rare event, right? So in here, we no longer rely on those accident data, but we actually use the safe trajectory data. So if we do something like that, and we do comparison in terms of the time that we need to compute the ranking of the different systems, this is our method. And this strive is a pure machine learning based method that's designed for this kind of assurance. So we can actually compute much faster. This is the time that we need. This is the time that they need without the training time. So that's just inference time. So I think sometimes in machine learning, they hide the inference time, which sometimes takes a while. So we do test not just on pedestrian example, but also on trying to merge in a lane. So these are the adversary. These two cars here are the adversary cars that we control. And yes, so that's an example of how collision happens. And we also compare this with what's called Kara leaderboard. So this Kara is a high fidelity simulator for autonomous car. So what people can do is that they can submit their software there, and then they can test how safe is their software. In order for them to do that, they need to hide the testing scenarios, because once the testing scenarios is found, any machine learning technique will be able to beat it. So in our case, we don't need to hide the testing scenario because we actually account for the unknown behavior of the cars. So this is the result that we get. And these are on different road condition, wet and dry. These are the different systems. And it turns out that what we get has the same trend as what the Kara leaderboard has. So that's, of course, many more work is needed to validate our results. Many more work is needed to check and verify. But it seems promising. So with that, basically, I've presented that with certain decision-making under uncertainty, sequential decision-making under uncertainty framework, we can actually start developing robots that are reliable, robust, and resilient. And it turns out the exact same approach can be applied to the assurance of autonomous systems as well. But of course, the modeling needs to be substantially changed. And just if you forget everything I say, perhaps just remember this, that I think we have made quite significant progress on POMDP ability to solve problems, at least in the robotics domain, and maybe we can start applying them. And of course, none of this would have happened without the work of many of my postdoc students and collaborators, and without the general support. And we are also hiring. So if you are interested in this kind of problems, let me know. We have immediate position to fill, and perhaps I will stop here.
Okay, thank you, Hanna. This was really impressive results, I must say. I mean, really interesting. And I would like to open the floor. We have plenty of time for questions. Open the floor to the audience if anybody has any questions for the speaker.
So hello, thanks for the great talk. So so I was wondering, well, I apologize if it is a very trivial question. So how hard it is to get this transition function?
Okay, that's a very good. Okay. That's a very good question. So basically, the question becomes, how do we model this, right? The transition. So from our experience, is actually transition and observation function are not that difficult to model. One of the things that makes it easier is that in POMDP, as I mentioned, you don't actually need to have the exact correct transition function. So even if those conditional probability are slightly off, usually as long as the support are somewhat correct, that's in practice is still working quite well. Right? So that's one thing. Now, having said that, the reward function is actually a bit harder to construct. Yes. But these days, so one of my postdoc is actually looking into learning the transition function. And it seems that's where we can nicely integrate this kind of methods with the learning. Each other brings their own strength, right? So the POMDP still gives some kind of guarantee of the performance of the safety, and then the learning provides the learn of the models. Yeah.
Questions for the speaker?
Should I go? Okay. Thanks very much. Two questions. First, do you have an intuition why, or theoretical understanding why, even if you get the transition probabilities not quite right, the thing still works well? That's the first question. And the second related is, are you also using probabilities to model human behavior? And if not, how are you handling the sort of what's often called unmeasurable uncertainty by decision theorists? Thanks.
So for the first one, one thing to note is that, as I mentioned earlier, we didn't actually get the absolute optimal solution. So I think if we want to get the absolute optimal, that would matter. But because what we are looking for in many cases is, well, I need to be able to be reliable and robust, and it seems that does not require the optimality. Even if we have some kind of approximation of the optimality, the fact that we account for the uncertainty and the forward possibilities of the different actions, different observations, that helps a lot already. Right? So that's one thing. So now, with respect to accounting for human, yes, to some extent, there are also works that tries to do that. So basically, when we are dealing with the human, the question becomes, how do you generate those distributions, right? And that goes back to, well, if we can somehow model somehow get the support right, in many cases, that's already helping in terms of the robotics problems. But as I mentioned before, we are not aiming for the absolute optimality. I think that's the main key why we can get away with many. Yeah.
Thanks, Hannah, for the amazing talk. So if I'm looking at the robotics literature these days, I'm going to see foundation models, vision language action models, diffusion planning, right? And you're talking about POMDPs. So is that just a parallel universe that's not going to work out, and you think this is going to work out? Do you think there's a merger? What's your view on all this other work that you didn't discuss?
Yes, thanks, Scott. So Okay, one thing I want to mention, robotics problem is a hard problem as it is. So I will take all the tools that is available. That I'm not going to say you have to use this, right? So I think what I wanted to say is there is a place for all the different tools. For instance, we are actually looking into diffusion model to learn the transition function. And that seems, at least some preliminary work seems to indicate that seems reasonable. We need to work on that to make it faster too. Uh, and then if we look into the manual imitation learning, that the robotics, usually the successful learning method there are imitation learning still today. And so if we look into that, one of the issue is the generalization. So basically, they need to be trained on data on the same robot. So if you change robots, for instance, then you basically need to get additional data for the particular robot you are working on, right? And then the type of scenario is also quite limited. That's one of the reasons if we take, for instance, the general bias RL, for instance, I think the performance is still somewhat low if you change different tasks, right? If you have multiple different tasks and you train on different tasks. So now, I think with POMDP, it would help in terms of the generalization. So the reason for that is that one way that we can view learning, in particular reinforcement learning, is as this Bayesian reinforcement learning that can be viewed as a POMDP point of view of how to systematically solve RL. And in there, the models becomes part of partially observed systems. And so then if we utilize our knowledge that, okay, so if I don't have the perfect understanding of the model, so basically my belief has not converged to a single state, I'm still fine. And so that allows me to be more relaxed on how good is my model. And what that means in the end is that, well, I might be able to use this for generalization as well. So that's one thing. Now, the second one that I wanted to mention is that that's why I'm careful with using the term sequential decision making rather than planning. That's because I do think there's room for integrating the two. So I'm not in the camp of everything needs to be in the POMDP planning or everything needs to be in the learning, right? And POMDP itself is a framework. So we can solve it using planning, we can solve it using learning, we can solve it using integrated planning and learning. So that's my view. Does that answer your question?
Yeah, thanks. I think you hit on a key point. I think we've lost explicit uncertainty in the foundation model age, and we need to get it back, especially for robotics. Yeah.
Hi. I have a question. From search perspective, when you have a problem that's like, for example, when you have a very large map, in some sense, it's not as bad as you have like a lot of degree of freedom, because your branching factor just dies. And then, so I'm just wondering, the example you showed, for example, the robotics arm, it has 6 degree of freedom, but scooping candy, like, I'm just saying, like, maybe it doesn't need all 6 degree of freedom, and in fact, I think most of the cases you don't need all the degree of freedom. Is it possible to just like limit some degree of freedom?
Yes and no. So yes and no. The reason is that if you work in open space, you might be able to reduce the degrees of freedom to just very small number, and then you do this kind of behavior, right? If we start wanting to operate around obstacles, then you do need the ability to do some kind of maneuvering, right? So that's the difference. So that's why I was for us in motion planning, we do want to operate near obstacles, and that usually makes difference. So perhaps let me try to see if I can find the. Okay. So if I want to be able to do some kind of maintenance work in this kind of plan scenario, then I do need to be able to go behind, for instance, right? So that one, I cannot get away with lower degrees of freedom. I need the maneuverability, right? So similarly, if I have this, if I need to be able to go in from the back, for instance, because of occlusion, for instance, then I do need that as well.
Thank you, Hanna, for the wonderful presentation. I have one question regarding robotics side. For example, how current POMDP online method can deal with uncertain action durations. For example, one action may be just several seconds, but some actions may take several minutes. And moreover, with the current powerful online method, can we try to integrate control and planning part together? Because usually previous robotics system have a individual like control module, perception module, planning module, but since we can deal with like enormous action space, can we just try to merge those together with the POMDP framework? Thank you.
Okay, so basically, for the second question, yes, definitely. So one thing to be careful to, the different levels of the hierarchy gives you some kind of abstraction that can make problems easier, right? So I think there's benefit to it, but perhaps in the way we do the integration, that's the question, right? So I don't have that in this slide, but I think if we start being able to seamlessly integrate the different components, the perception, the low-level control, the motion planning, the task planning, if we can do that in a seamless manner, then we can start reducing accuracy requirements, for instance, in the SLAM, in the simultaneous localization and mapping. So it makes that problem a little bit easier, right? Because we push to the decision making that we say, well, now if I don't have a perfect model of the environment, I can still do well, right? So that's pretty much where we can gain, I think, right? But I totally agree of the integration, but I'm not too sure if everything then becomes a huge giant omni. Maybe I won't say no. so that's one thing. So what's the first question that you have? Okay, right. Yeah. Yeah. So uncertain action duration, I think a proper way to do that is to move to what's so-called semi-Markov process. So you start having continuity in time domain as well, right? But another way is when we are running execution, so basically, like even in this example, usually we will start planning for the next step the moment we give the action to the robot to execute. So basically, in that sense, it becomes like a discretization of time of where you are, right? So you can actually leave, if the action has not ended yet, you can leave it be and just continue with the planning, and then and then later on you pass it to the robot once they are ready. So it's a little bit different model, but it's still doable.
I think we are just at time. Thank you very much to the speaker, Hanna Kurniawati, for this excellent talk.
Thank you so much. Thank you.